is nothing to worry. This is the 16th lecture, and we are going to talk of natural response and poles and zeros, and we are also going to introduce the forced response of electrical circuits. In terms of the poles and zeros, you know that if I am given a two-terminal network, as we have been discussing, and I find out the impedance Z of S, by definition it is the ratio of voltage to current, provided one of them is of the form e to the st, and we had shown that Z of S is in general of the form k multiplied by a polynomial p of s divided by another polynomial q of s, where we have taken care that the leading coefficient of both p and q are unity. These coefficients are absorbed in the constant k, and you know that a polynomial of degree m has m number of roots. Therefore, it can be written in terms of s minus zi, where I goes from, let's say, 1 to m, divided by I equal to 1 to n s minus pi. And in general, if you are interested in finding the current by short circuiting the input terminals, that is, if you short circuit this and you want to find the current flowing through this, then it is the zeros which come into play. And therefore, if the terminals are short circuited, then the natural current response shall be of the form summation ai e to the power zit, I equal to 1 to m. The poles do not come into play, where you have to determine the constants ai from the initial conditions. On the other hand, if you wish to find out the response of the voltage across these two terminals, then you leave it open and you determine the voltage across this. Then the voltage response V of t, natural voltage response, shall be determined as Bj e to the power Pjt, where j equals to 1 to n, and we had assumed that none of the poles or zeros are repeating. We assume that they are distinct. If they are repeating, then we know what to do. We shall have to modify accordingly. But the point that I want to emphasize is that if you can find out the poles and zeros, the frequencies of natural response, either of voltage or of current, are immediately determined, and you can write down the form of the natural response immediately, where the constants have of course to be determined from the initial conditions. I repeat that if it is the current, then you will have to look at the impedance zeros. If it is the voltage, then you will have to look at the impedance poles. And the underlying reason we have already explained, that the relation is V equal to Zi, and therefore if Z equal to 0, then V equals to 0 independent of what I is. And similarly, in the case of the open circuit, I take the relation I equal to Y times V, and therefore if Y equal to 0, which means the poles of Z, if Y equals to 0, then I equals to 0 irrespective of what V is. I equal to 0 means an open circuit, and through an open circuit a current cannot flow. So these are the theoretical or conceptual links between poles and zeros and the natural response of the circuit. We take in quick sequence a few examples to illustrate the points that we have been making. Let's consider a circuit like this. There is a voltage V which is connected through a switch S. The switch opens at t equal to 0 to the points A and B of a two-terminal circuit, and the circuit consists of a capacitor C, a resistance R, and an inductance L. Okay. What you are required to determine is if the switch is thrown open at t equal to 0, what is this voltage V of t? What is this voltage V of t for t greater than equal to 0? This is what has to be determined, and therefore it is a case of open circuit or natural voltage response. So we find out the impedance looking from A to B, impedance looking into the network from the terminals A and B. Alright, so we find out GAB, and what will be of concern are its poles. Is that clear? Because we are trying to find out the natural response of the voltage, and therefore this is 1 over SC plus SLR divided by R plus SL. This is the total impedance, and this is equal to, now look at the simplification, SC R plus SL, then S squared LCR plus SL plus R, alright, which I can write in the standard form by taking LCR out from here and CL out from the denominator. Then we get Z of S as equal to R times S squared plus S divided by CR plus 1 over LC, and here I shall get S times S plus R by L. Is that okay? Now we are trying to find out the natural voltage response, and therefore our natural frequencies are the poles, and therefore I know, without doing any more manipulation, I know that V of t shall be of the form A e to the power, where are the poles? One at the origin and the other at minus R by L. So e to the power 0 times t is a constant 1. So A plus B e to the power minus t by what? L by R, okay, or minus RT by L, where there are two arbitrary constants A and B. They have to be found out from the initial conditions. Alright, the question of initial conditions has to be thought about a little, as we shall see in one particular example. I will leave the rest of the example, finding A and B from initial conditions, to you. Let's quickly look at another example. One of the examples I will completely do. The second example is the same one, but with a little bit of a difference. We have this switch thrown open at t equal to 0, and then there is another switch which is closed at t equal to 0. Alright, there are two switches which are operated simultaneously. One is thrown open and the other is closed. The circuit is the same, that is, we have a C, then an R, and an L. And here, to bring the point a little more into focus, let us say that the values of C and others are 0.1 farad, L is 0.2 Henry, and R is 1 ohm. The question is to find out the current. To find out the current in the resistance, that is this current. Just to bring variety into experience, the question is to find this current. Now, if it was to find this current, that is through the capacitance, then we know this impedance would have done the job. The impedance between A and B, which you had already found out, it would have done the job. But no, the question is to find a current in this resistance, and therefore the artifice or the instrument that we use is to break the circuit here, and then we shall find the impedance between these 2 points. Then we shall make a short circuit and find the current. Is that okay? So our circuit then shall look like this. There is a break here, R, and we have an L, and we have a C here, which ultimately becomes shorted through this switch. there is an initial voltage on the capacitor, which would be exactly equal to the voltage that is at the source, all right. That is part of the initial condition which you can find out. That is Vc0 minus would be equal to Vc0 plus, IL0 minus, which is equal to 0, shall be equal to IL0 plus, all right. But the point is, since we are trying to find out the current through the resistance R, we find out the impedance between these 2 points. We make an artificial break, find the impedance, and then find its zeros, all right. The impedance obviously is equal to R plus the parallel combination of L and C, that is SL divided by S squared LC plus 1, all right, which I can write as S squared LC plus 1, S squared LCR plus SL plus R. I write it in the normalized form as Z of S equals to R S squared plus S 1 over RC plus 1 over LC, S squared plus 1 over LC, all right. This is Z of S. And what I have to find now, since we are trying to find the natural current response, we are going to concentrate on the zeros of the impedance. Now, if I put the numerical values, zeros of Z of S shall satisfy S squared plus S 1 over RC, that is 10 times S, and 1 over LC is 50, that's equal to 0. These are the 2 zeros. And if you look at them, S12, well, minus 5 plus minus square root of 25 minus 200, no, I'm sorry, 25 minus 50, is it okay? Yes. So this is equal to minus 5 plus minus j 5, is that okay? Minus 5 plus minus j 5, and therefore the current in the resistance, natural current response, will be obtained as some constant A1 e to the power minus 5 plus j5t plus another constant A2 e to the power minus 5 minus j5t. This will be the current response. But you know this can be written as B e to the minus 5t sine of 5t plus theta, where the two constants B and theta have to be found out from the initial conditions, all right. That part, as I said, I am going to leave to you. I am going to take a third example which I shall do completely, but this should be easy to follow. Do you understand? Let me go back and explain to you the method. The method is that if there are 2 points across which you want to find the natural voltage response, then you find out the impedance between those 2 points and look at the poles. If you want to find out the current through short circuit between 2 points, then you look at the impedance between those 2 points. For example, here there was no break, we made a break. We want to find this current, so what we said is we will make a break here, create 2 points which when short circuited shall give me IR, the resistive current. So what we did was we found that the impedance looking into these 2 points and concentrated on the zeros, all right. Zeros of Z of S will give you natural current response frequencies, poles of Z of S gives natural voltage response frequencies.
Sir,
yes.
Where should we make the cut?
Where should you make the break? Yes. It doesn't matter where you do.
In this circuit it doesn't matter. Suppose we have a capacitor in series with the resistance.
Oh, the current has to be the same in both. Suppose you have, this question is this, suppose you have to find the current in this. When you make a break here, or you make a break here, or you make a break here, it doesn't matter. The zeros of the impedance shall be the same. Alright? It will not matter where you make the break. Is there any other question? Let me take the third problem, which as I promised I shall solve completely. A slightly tricky problem. We have a capacitance and a resistance. We will say this is C2, but C2 is equal to C, the resistance is R, and then I have a series combination of a capacitance C1 and a resistance R. C1 is also equal to C. We are distinguishing between the two because we shall charge one of them. What we will do is VC1 is this voltage, VC1 at 0 minus, we will say this is V0. We have charged this capacitor to a voltage V0. C2 is left uncharged. C2 initial charge is 0. And then what we have is there is a switch here. There is a switch here which is closed at t equal to 0. This is closed at t equal to 0, and it is this current. It is this current that we wish to find out, the current I. Alright? This is a situation in which one should find out the impedance between these 2 points. Impedance offered to the switch before it closes. Alright? Then by shorting this we find out the current. So let's find out the impedance between these 2 points. This would be given by R plus 1 over SC, R plus 1 over SC, plus the parallel combination of these two, which is R divided by S, C, R plus 1. I have avoided one algebraic step. With a little bit practice, you shall be able to do this. If I simplify this, I get R. Again, I am omitting a couple of algebraic steps, which you can fill in. In the denominator, I shall have S times S plus 1 over CR, and in the numerator, I get S squared plus 3S plus 1. Alright? And since I am trying to find the natural current response, it is, had I assumed values? Yeah, I have assumed values. Okay, I have assumed that C is equal to 1 meg, C is 1 microfarad and R is equal to 1 meg. Let's do that, 1 meg. So the product RC is equal to 1, what is the unit? Product RC is unity, 1 microfarad and 1 meg, 1 second. CR is the 1 second. Then this should be equal to 1. Alright. R is 1 meg, 10 to the 6 ohms, 10 to the 6 ohms, alright. Meg is mega ohms, that's correct. So my natural current response then shall be determined by the zeros of this, S squared plus 3S plus 1 equal to 0, the zeros of the impedance, and these zeros happen to be, is a quadratic, nothing difficult, minus 0.38 and minus 2.62. The sum of them is equal to 3, it has to be. The product of them has to be equal to
1.
Plus 1, that's what it is. Alright. So my current response I of t shall be equal to A1 e to the power minus 0.38 t plus A2 e to the power minus 2.62 t. Alright. Now comes the question of initial conditions. Alright. Let's go back to the circuit. At t equal to 0 minus, this voltage VC1 is V0. I have assumed a value also. Let V0 be equal to 20 volt, alright. Then this voltage is 20 volt at 0 minus. The current here is 0, there is no current. This voltage is 0 because this is uncharged. At t equal to 0 plus, what does this see? What does this capacitor C1 see? It sees a resistance R and an R, but paralleled by an uncharged capacitor. What is the voltage difference across an uncharged capacitor? Zero. And therefore this behaves like a short circuit, and therefore this capacitor C1 sends a current through R in this direction, in the opposite direction, which is equal to 20 divided by R, not 2R, only 1R, because this R gets short circuited, and therefore I of 0 minus, I of 0 plus shall be equal to minus, you understand the minus sign? Capacitor is charged like this, so it tries to send a current in this direction, whereas my I assumed in this direction. So it is minus 20 volt divided by 1 meg, which is simply 20 microamperes. Alright. So one of the conditions is that 20 times 10 to the minus 6 shall be equal to A1 plus A2. That's one condition. I require another condition to be able to evaluate both A1 and A2. Yes, Aditya?
So you will put 20 or minus 27?
Quite so. I must put this equal to minus 10. Thank you. This is one of the initial conditions. Now let's look at the other initial condition. That will turn out to be interesting. How to find the other initial condition? You see that at t greater than 0, greater than equal to 0, the circuit is like this. You have a C, you have a R. Okay, did I call this C1? I called this C1. Okay, C1 R, or this was C2. Alright, C2 equal to C. Then I have a C, C1, which is equal to C, and then an R. And this is shorted. This is the current I. Alright. Obviously, KVL must be obeyed. But before I write KVL, this current I finds two paths. You have to be very careful in solving such problems. It finds two paths. One of them is through the capacitor. Let's call this I1, and the other path is I2. Alright. So the voltage drop from this point to this point would be simply 1 over C2 integral I1 dt. Is that clear? Is that okay? From 0 to t. At any instant of time t, the voltage VC2 plus minus is simply given by 1 by C2 integral 0 to t I1 dt. Is that okay? And this current I then flows through C1 also. So what would be this potential? VC1 shall be equal to 1 over C1 integral 0 to t I1 dt, then
Plus I2.
I dt, plus or minus, that is the question. Unfortunately, it is plus, because I will explain. The initial voltage was V0 in this polarity, and when the capacitor is getting charged like this, it is adding to V0, so it is a plus V0. You have to remember this. Alright, it is plus V0. So this is VC1, and what is VR? VR is simply IR, and the sum of the three, VC2, I am not taking the drop across R. Why? Because it's the same as VC2. Is that clear? It's the same as VC2. So VC2 plus VC1 plus VR, that should be equal to 0. Alright? And therefore my equation becomes, now I need not distinguish between C1 and C2 anymore. I can say 1 by C integral 0 to t I1 dt plus 1 by C integral 0 to t I dt plus V0 plus IR is equal to 0. Alright? We convert this into a differential equation to start with. So what I get is I1 plus I, if I differentiate both sides. Is there a question on this? No. I1 plus I divided by C, even if you had made a mistake in putting the sign of V0, it would not have mattered, right? Because you are differentiating, differential coefficient of V0 is 0, so plus R I equal to 0, which means R di dt. Thank you. And therefore di dt is equal to minus 1 over RC I1 plus I. Is that clear? Now at t equal to 0, di dt t equal to 0 is equal to minus 1 over RC, actually 0 plus. Now what is I1 of 0 plus? This is same as I, because it behaved like a short circuit, and therefore this is twice I of 0 plus. And what was I of 0 plus? 20 microampere, and therefore this would be simply minus. Okay, so it would be plus 1 over RC times 40 times 10 to the minus 6, and RC is 1, and therefore this is simply equal to 40 microampere per second. Okay, I was waiting for this, and therefore I get A1 plus A2. What was this equal to? Minus 20 times 10 to the minus 6, and di dt at 0 plus. What will be di dt 0 plus? Minus 0.38 A1 minus 2.62 A2. This will be di dt at 0 plus, because I was A1 e to the minus 0.38 t plus A2 e to the minus 2.62 t. I differentiate this and put t equal to 0. This should be equal to minus 40 times 10 to the minus 7. Pardon me? Plus 40. Now you can solve for A1 and A2. Alright? I'll leave that part to you. But I've shown how to evaluate the constants, how to get the differential, how to get the initial condition. Each problem, there is nothing routine about it. Each problem has to be looked into differently to find the initial conditions. And you must remember that if it is a voltage or a current, it doesn't matter. One of them shall involve the values at t equal to 0, current or voltage. The other has to involve the differential coefficient. It has to involve the differential coefficient. Why? Because there is no other time at which the voltages or currents are known. At infinity, for example, natural response will automatically die. You see, you look at A1 e to the minus 0.38 t plus A2 this, at t equal to infinity it has to be automatically 0. So this is no condition, no boundary. You will have to look into the differential coefficient, and that is the clue. If it's a capacitor, then you look at dV dt. If it's an inductor, then you look at di dt. But even that is not obeyed in this particular case, because we had to find out a di dt, and you shall have to think about this to be able to find the initial conditions. It would be a good exercise to try the previous two problems where I simply obtained the form of the solution and left the rest to you. It would be a good exercise to try the other two problems and solve them completely. It is now time to go into an introduction to forced response. So far, what we have considered is natural response. That is, we consider a circuit in which we consider a circuit in which there are energy storage elements, where energy is initially stored either in the form of charge on a capacitor or flux in an inductor, and then we cause the excitation or the reason for the initial charge removed, and find out what happens to the currents and voltages in this circuit. This is what we call natural response. And you see that the natural response is very closely linked to the poles and zeros of an impedance function or admittance function. Admittance, after all, is the reciprocal of an impedance. Now, it turns out that this artifice of impedance function or an excitation of the form of e to the st is extremely useful in finding the response of a circuit to an external excitation, that is, to a force, to a forcing function. It is the same artifice that shall work, and in doing so, in considering forced response, we shall consider, because we are considering basically linear circuits, we shall consider the two independently, that is, natural response and forced response separately. Then we shall combine the two. All right. So far we have considered natural response. So when we shall discuss forced response, we shall assume that the circuit is initially dead. In other words, the circuit, even if there is a capacitor, the capacitor is initially uncharged. If there is an inductor, the inductor is initially unfluxed, or it does not have any flux. We shall do that for simplifying reasons, and then later we shall consider the total response. That is, we shall add up the natural response and the forced response subject to the constraints that appears between them. But in the whole process, as you shall see, e to the st plays a very dominant role. E to the st, the exponential function that we have been considering so far, plays a very dominant role. For example, if we have, let's say, a series combination of resistance and inductance, all right, and we want to force it, that is, the inductance is initially relaxed, and we want to force a current through this, let's say I0 e to the minus alpha t, all right. Then this is a special case of I0 e to the st with s equal to minus alpha, and therefore the voltage response between the two, voltage response or the voltage drop across the RL combination, the forced voltage drop, all right. This is a drop occurring due to the current I0 e to the minus alpha t passing through this series combination, will be given by R times the current. So R I0 e to the minus alpha t minus alpha I0 e to the minus alpha t times L di dt, and therefore this is R minus alpha L I0 e to the minus alpha t, and you can see that R minus alpha L is simply the impedance of this combination for S equal to minus alpha. The impedance in general is R plus SL, but S here is minus alpha, and therefore this is the impedance. All right. A very special case of the exponential excitation occurs if S equals to 0. If S equals to 0, it is a constant current, and therefore d dt would be 0, and so the drop would be simply R times I0. All right. Therefore, e to the st excitation can also take care of DC conditions by putting S equal to 0. For example, if there is a resistance R, then the impedance of the resistance is simply equal to R, whatever the value of S is, irrespective of the value of S. All right, whether it is e to the st where S is 0 or complex or real, it doesn't matter. All right. On the other hand, if you have an inductance L, then you know its impedance is SL, and therefore at DC, when S is equal to 0, the impedance is a short circuit. All right, short circuit at DC. ZL 0 is equal to 0. On the other hand, if we have a capacitance C, the impedance of the capacitance is 1 over SC, and therefore at DC the impedance is infinity. In other words, it is an open circuit at DC. Open circuit at DC. It also can be a short circuit, but then you have to make S equal to infinity. At infinite frequency, the capacitor behaves like a short circuit, but at DC it behaves like an open circuit. Alright. One very special case of the excitation e to the st occurs if S is a purely imaginary quantity, if S is equal to j omega, and then what we get is this excitation becomes a combination of a sine and a cosine, j sine omega t plus cosine omega t. Alright, e to the st with S equal to j omega becomes a combination, becomes a real part which is cosine plus j times an imaginary part which is sine. Now we go the other way around, that is, we argue that if the excitation is sinusoidal, how to bring in, how to marry it with the concept of e to the st, that is exponential function, or how to marry it with the concept of impedance. Then you see, manipulating sine and cosine functions is a difficult job. It is time consuming. You have to keep track of the sines, phases and all kinds of things, and therefore what we wish to do is to get a simplified concept. Somehow for sinusoidal excitation we would like to go to the impedance concept and see how things can be handled, and this is made convenient by the concept of so-called phasors. But before we introduce phasors, let's look at this sine wave or cosine wave a little more closely. If you have a complex quantity, let's say a plus jb, then one of the ways that you can represent this complex quantity is to mark a distance of a on the real axis, on the x-axis, and a distance of b on the imaginary axis, on the orthogonal axis or the y-axis, and then get this point where whose coordinates are a, b. All right. Then a plus jb, if a is considered as a vector and jb is considered as a vector in the perpendicular direction, then you can see that this a plus jb then represents this vector. All right. This is very well known to you. You have studied this in the high school. Now, this is the rectangular representation. You can make a polar representation by saying that if this angle is theta, the angle that it makes with the real axis or the x-axis, if this angle is theta and the length of the vector is capital M, then you can represent a plus jb as capital M angle e to the power j tan inverse tan theta is b by a, so tan inverse b by a. This is a polar representation. We call this e to the power j theta. Theta in fact is tan inverse b by a. All right. Let's look at this a little more closely. We have a vector m which is shifted from the real axis by an angle theta. Now such a vector we shall represent as m bar. The bar will mean that it is a vector, and we will not use the arrow because arrow is used for actual electric and magnetic field vectors. We shall reserve that for later use, if at all there is a use for you. Now this will mean that it is a complex quantity, m bar, and when I write m, I mean its magnitude. So m bar is m e to the power j theta, or another way of writing this is m angle theta, and this m bar is called a phasor. This vector is called a phasor. Well, this is an artificial way of looking into things, artificial way, because we are representing the orthogonal component on the y-axis, and we say that is our imaginary axis. all right. And so we are combining the two, getting a representation of a complex quantity in terms of a phasor. In this context, a vector is replaced by the word phasor, but phasor has a special interpretation and connotation, or let's say a convention in the case of electric circuits, which we shall come to in a moment. But suppose this vector rotates anti-clockwise with an angular velocity omega, all right. It started from here, then it starts rotating in the anti-clockwise direction with an angular velocity omega. So after time t has elapsed, the vector takes this position where the magnitude is still m, but the angle has increased by the amount omega t, and therefore this phasor, well, this vector represents the complex quantity capital M e to the power j omega t plus theta, and you see that its projection on the real axis is m cosine omega t plus theta, which is our familiar sinusoidal voltage or current, and its projection on the imaginary axis is m sine omega t plus theta, which also can represent a sinusoidal voltage or current as generated by an alternator in the laboratory, all right, as generated by an alternator. And therefore this concept of a rotating vector is very much utilized for finding the response of electrical circuits to sinusoidal excitation. And in this context we now make a formal definition of a phasor. Suppose we have a voltage V of t equals to Vm cosine of omega t plus theta. Cosine, we take cosine as our standard reference, and we take sine as the imaginary, we represent sine on the imaginary axis. It can be other way around, there is nothing sacred about it, all right. So it's only because Vm cosine omega t plus theta can be represented as the projection on the x-axis of a vector Vm e to the power j omega t plus theta. That's why we take this as the reference. Now we write this as, you see, this by itself is not a complex quantity. It is the real part of a complex quantity, real part of Vm e to the power j omega t plus theta, all right. And Vm is the peak value. If I represent the root mean squared value by capital V, then it is simply root 2V, real part of root 2V e to the power j omega t plus theta. It is conventional to write this as the product of two quantities. One is V e to the power j theta, and the other is root 2 e to the power j omega t, all right. Now if this voltage is applied to a linear electrical circuit containing resistors, capacitors and inductors, then all currents and voltages shall be sinusoidal. They shall be, you will be able to write them as some constant multiplied by cosine omega t plus some other constant phi, or sine omega t plus phi, all right. And therefore all of them, all currents and voltages shall have this as the common thing, root 2 times e to the j omega t, all right. All currents and voltages in the circuit shall have this. Therefore this quantity V e to the j theta is as if an identifying factor, as an identifying factor for the voltage V of t. If I have another voltage which is 90 degree out of phase with this, then all that I do, I shall add e to the power j theta plus 90, all right. If the magnitude is different, I will take the differing magnitude there, okay. So this quantity is known in the electrical circuit analysis context as a phasor, and therefore the representation of V of t, if we are considering only sinusoids of frequency omega, then the representation of V of t, Vm cosine omega t plus theta, is, although it's a real quantity, it is represented by a complex number which we call V bar, and we call it is the voltage phasor, which is equal to V e to the power j theta. In effect, this means that we have a vector whose magnitude, whose length is V, and whose angle measured with respect to the x-axis is theta. Alright, so all sinusoids now can be represented as a phasor. And you see, what we had was a time function. What we had was a function of time, cosine omega t plus theta, and we have now divorced or got rid of the time. Alright, we have got rid of the time. We have got rid of the factor omega t, because we argue that in the complete circuit all currents, all voltages shall have root 2 e to the j omega t common, and therefore somehow we have got rid of this, and the fact that it is the real part of a complex quantity, that also we shall ignore, because all currents and voltages can be expressed as real part of some quantity, and therefore this quantity V of t, which is very much a real quantity, is now being transformed into a complex number. As far as this is concerned, this is simply a complex number, V cosine theta plus j V sine theta. The time dependence, the frequency content omega, they are all completely given up. That it is the real part we also forget. So what we will do is, given an excitation which is a voltage or a current, doesn't matter, which is sinusoidal, we shall represent it by a phasor, and then we shall investigate all currents and voltages in the circuit of phasors, and we shall manipulate only phasors. Finally, when we get, say, let's say the desired quantity, it could be, for example, a current, and you say the current to be determined, maybe this is of the form e to the I0 e to the power j alpha. If you see, if this is the final desired quantity obtained by manipulating the circuit in terms of phasors only, then we shall say the output current, corresponding current, must be I0, real part of I0 e to the j alpha times root 2 e to the power j omega t. That's how we can bring back the actual quantity, real quantity. So it will be root 2 I0 cosine of omega t plus alpha. This would be the actual quantity that you will measure if you put an oscilloscope there. Alright. In between, therefore, we go through a transformation from the time domain into this complex domain of numbers, and this greatly simplifies calculations. To take a couple of examples, let's consider a phasor, let's say 10 root 2 cosine omega t. This is the actual voltage or current, let's say Vt. What would be its phasor? Its phasor would be 10 e to the power j 0 cosine omega t. There is no theta, theta is 0, so this is its phasor representation. If we have, let's say, 10 cosine of omega t plus pi by 6, then its phasor representation would be 10 by root 2 e to the power j pi by 6. This is its phasor. Alright, if I call this, let's say, I1, let's say these are current to bring variety into experience, then we shall represent this as I1 bar, we shall represent this as I2 bar. Suppose I had a 20 root 2, let's say this is a voltage, let's say V1t, 20 root 2 sine of, let's say, omega t plus pi by 6. Now sine can be written in terms of cosine by subtracting 90 degrees. Now cosine of 90 minus theta is equal to sine theta. Therefore I could write this as omega t plus pi by 6 minus pi by 2. Alright. Now if you change this number pi by 2 minus theta or theta minus pi by 2, it doesn't matter, and therefore what would be the corresponding phasor? 20 root 2 is gone out, e to the power j pi by 6 minus pi by 2, which is minus pi by 3. So this would be your V1 phasor. Is that okay? Let's take another simple example. Suppose we have two voltages, let's say V1 and V2, which occur across, let's say, series combination of two circuit elements. Let's say V1 and this is V2. We have to find the total voltage V. Total voltage V is equal to V1 plus V2. And suppose this is a circuit having a sinusoidal excitation. And suppose the forced responses for V1 and V2, let's say V1 is 150 root 2 cosine of 100 pi t minus pi by 6. Suppose V1 is this. You can see that it is a 50 Hertz sine wave, twice pi f is 50, that's why 100 pi t. And suppose V2 is, let's say, 200 root 2. I am showing the RMS quantity specifically. This is the peak value, divided by root 2 is the root mean squared value. Let's say this is cosine of 100 pi t. You must remember these frequencies must be the same, omega must be the same throughout. Alright, let's say this is plus pi by 3, and I want to find out V in terms of a single sine. Alright, now instead of single sine or cosine, instead of manipulating this, taking this as the real part of some quantity, imaginary part of some quantity, no, r cosine theta, r sine theta. You see, these are not equal, the phases are not equal, and therefore what you will have to do is, if you want to do it algebraically or trigonometrically, then you should have to expand this, you should have to expand this cosine, collect all the cosine terms together, collect all the sine terms together, then put the coefficient of cosine terms as r cosine phi, coefficient of the sine terms as r sine phi, then you will have to combine. Now you will see how easily we do this. We represent this by a phasor. V1 phasor corresponding to this is simply 150 e to the minus j pi by 6, and V2 phasor is 200 e to the power j pi by 3. Alright, we represent them in the complex plane. E to the minus j pi by 6, 150 is, let's say, this is V1 phasor. Then this angle is pi by 6, and then the other phasor is 200 e to the j pi by 3, let's say this V2 bar. This length is 200 and this angle is pi by 3. Now we add these two phasors, alright, because the only information that we have gotten rid of is root 2 e to the power j omega t. This is common to both, and therefore you can add them up. Do you see the logic? You add them up and take the real part. How do you add them up? You can do this by means of parallelogram of vectors. You can do this, measure this and measure this angle theta, then you will be able to find out. Suppose this is VR, suppose the resultant is VR, which is VR angle theta, alright. If it is so, then you know what is the resultant. Resultant would be root 2 VR cosine of omega t plus theta. As simple as that. Question is, how accurate is the graphical measurement? You represent it on a graph and you measure it. How accurate it is? Well, you don't have to worry, because you could do it analytically also. Let's look at that. The phasor V1 is 150 e to the minus j pi by 6. I can write this in terms of its rectangular coordinates, that is 150 cosine pi by 6 minus j 150 sine pi by 6, and the result is 130 minus j75. Similarly, you represent V2 by means of, in terms of rectangular coordinates, this will be 200 e to the j pi by 3. So 200 cosine pi by 3, that is 100, plus j 200 sine pi by 3, 200 times root 3 by 2, which comes out as 173. Then what you do is V1 bar plus V2 bar, you are making vector addition by parallelogram vectors. So you add the real parts and add the imaginary parts. So you get 230 plus j 98. This, now you convert it into the polar form again. That is square root of 230 square plus 98 square, and angle is tan inverse 98 divided by 230, and the result is 250. The angle is 23 degrees 0.1, and therefore the resulting voltage shall be 250 root 2 cosine of 100 pi t, we bring back the frequency, plus 23 degrees 0.1. That is the final result. And you see the tremendous simplification that it offers. Next time, tomorrow, we shall consider how this phasor representation reflects in the impedance function.